This tutorial will focus on your lab skills. Many of the labs you perform will involve data collection and data analysis. You will often be required to plot a graph and then determine the relationship between the variables in question. By using your knowledge of physics, you should be able to predict not only the shape of your graph, but also interpret any slopes or intercepts. By now you will be familiar with the linear relation y equals mx plus b, where m is the slope and b is the y-intercept, and y and x are both the dependent and independent variables respectively. Y and x are the variables whose relationship you will be exploring in any lab activity. Let's look at a typical high school physics experiment that involves hanging a variety of masses from a spring and measuring the stretch. For this particular lab, the goal is to determine the relationship between the change in length, or stretch, of the spring and the mass. Before you begin the lab, try to determine what this relationship is using physics concepts you have already encountered. For springs, you will know that ideal springs adhere to Hooke's law. Hooke's law states that F is equal to K times change in X, where F is the force providing the stretch, in this case the hanging mass m, and change in X, or delta X, is the change in length of the spring, or stretch. K will be the spring constant. For this setup, the force responsible for stretching the spring is the force of gravity provided by the hanging masses. You will also recall that force of gravity, or Fg, equals mg, mass times gravity. We now have mg equals k delta x. When you go to plot the graph, the dependent variable will go on the vertical or y-axis. For this lab, the amount of stretch, delta x, is the dependent, since the amount of stretch depends on the hanging mass. Mass m will therefore be the independent variable to be plotted on the horizontal or x-axis. The trick is to solve your equation for the dependent variable. When we do, we get delta x equals mg over k, or delta x equals g over k times mass times m. We have now determined our theoretical relationship. Having collected the data, you then plot stretch versus mass and construct a straight, best fit line through the data points as shown. For any straight line, it is easy to determine both the slope and the intercept. After converting to standard SI units, we find the slope to be 0.1 meters per kilogram and the intercept to be approximately 0.002 meters. We are now prepared to determine the equation of our plotted line. This will become our experimental relationship. For any straight line, y equals mx plus b. Once we substitute in our slope and intercept constants and then replace y and x with the actual variables delta x and m, we ultimately get delta x equals 0.10 meters per kilogram times mass plus 0.002 meters. We are now in a position to compare the experimental to the theoretical equation. Our predicted or theoretical equation shows a direct relationship between delta x and m. Any direct relationship will present as a straight line that passes through the origin. In other words, the y-intercept will be 0. We can imagine our theoretical relation to look as shown. Comparing the constants, we see that our slope will be equivalent to g divided by k, as predicted by our theoretical equation. Our theoretical equation also predicts an intercept of 0. Experimentally, we observe a small intercept of 0.002 meters. Since this is close to 0, we may attribute this to experimental error. Finally, since g over k is equal to 0.10 kilograms per meter, We could then easily determine or calculate the value of the spring constant K, since we know that G is equal to 9.8 meters per second squared, assuming this experiment was done on Earth.